Welcome everyone, I'm Norman Weilberger. Today we're going to look at multiples of simple small numbers, like multiples of 10, multiples of 5, multiples of 4, and so on. This gives us a natural bridge between addition, which is what we've been talking about, and multiplication, which is the next operation that we'll be having a look at. It also gives us a chance to look at some larger numbers and talk about the names that we're going to give to some larger numbers. So last time we talked about even numbers. The numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, and so on. These are also the multiples of 2. Because this is 2, this is 2 plus 2, this is 2 plus 2 plus 2, this is 2 plus 2 plus 2 plus 2, and so on. Represented a little bit more geometrically by these rectangles. So 2 can be represented by this rectangle, which is a 2 by 1 rectangle. This 4 is represented by a 2 by 2 rectangle, 6 by a 2 by 3, 8 by a 2 by 4, 10 by a 2 by 5, 12 by a 2 by 6, and so on. So all of the even numbers can be represented by rectangles that have exactly 2 rows. So today we're going to look at multiples of bigger numbers, and we're going to talk then about the names of numbers a little bit more than we have already. So after the multiples of 2, probably the next simplest multiples are those of the number 10. And that's only because we're working in base 10, so multiples of 10 have a particularly simple representation and a particularly simple kind of arithmetic. So here is the pattern of multiples of 10. It's a reasonably simple pattern because you see just the ordinary pattern of numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on, repeated with an extra 0 at the end of everything. So how do we get this sequence? Well, the first one is 10, and then the next one is 10 plus 10. And that's 2 10s, or what we usually call 20. And then if we add 10 to that, well then altogether we have 3 10s, so it's represented by 3 0. We add another 10, and altogether we have 4 10s, so it's 4 0. And so on, 5 0, 6 0, 7 0, 8 0, 9 0. And then this number 1 0 0 representing 0 ones, 1 10, and 100. Because remember, once we have 10 10s, that's the same as what we're calling 100. Okay, so we're going to be concentrating mostly on these multiples of 10, just from the range 10 to 100 at first. So our first order of business is to give some names to these multiples of 10. Right now we have symbols for them, but we don't actually have names for them. So these numbers are important numbers and they get special names. Each one gets a special name. Just like the numbers from 11 to 19 or to 20 get a special name. This one we've already called it 10. This one here we call 20. The next one 30, the next one 40, the next one 50, the next one 60, then 70, then 80, then 90, and then this one we've already talked about, 100. Now, these names are a little bit arbitrary, but they're also obviously connected to the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see the 9 there, you can see an 8 there, a 7 there, a 6 there, kind of a 5 there, something like a 4 there. The 3 there is a little bit more dubious. The 2, well, there's a bit of a 2 there. And that's just 110 by itself. So these names are a little bit arbitrary, and we run into the same kinds of comments that we made about the numbers from 11 to 19. The fact that these numbers don't have really a logical names, that there's not an obvious pattern to this, means that students have to memorize these numbers. And that adds an extra layer of difficulty in learning arithmetic. In fact, I'll confess to you that when I was writing these things down reasonably quickly, when I got to 40, I wrote F-O-U-R-T-Y, until I looked at it and said, no, that doesn't look right. So if you don't do this a lot, it's easy to get confused. Is there a 4 there, like F-O-U-R, or is it 40? Remember 14, which was a similar kind of number. 14, 40, much the same. The 14 does have an F-O-U-R there, while the 40 doesn't. So you have to remember idiosyncrasies like that, and for a lot of us, remembering things for which there's no good reason is a little bit hard. Okay, so I did propose some alternate kind of naming system for the numbers 11 to 19. Let me go ahead and continue with that idea, that vein, and give some alternate possible names for these numbers. Obvious kind of names are 10, as before, and then 210, 310, 410, 510, 610, 710, 810, 910. That makes it completely obvious, completely clear what the pattern is, and there's nothing really extra that needs to be memorized. And I think there are certain languages in which this kind of system is used. And pretty clearly, students using this kind of nomenclature have an advantage over students who are forced to use something like this. I might say that English is not the worst language in this regard. French, which is a very beautiful language, of course, does have even more idiosyncrasies when it comes to naming these kinds of numbers. And I'm not sure about other languages. Probably there's quite a variety of logical consistency between various languages. It might be interesting to make a study of that. And see, for example, how it correlates to students' acceptance of early arithmetic. All right, so we'll, of course, stick with this primarily, but every so often I might throw one of these things in just for fun. So just keep in mind that we have a kind of an alternate possible notation for these. But if you're a student, you're going to have to learn these names for the multiples of 10. Very, very important. Once we have the names for the multiples of 10, from 10 to 100, then the remaining numbers from 20 to 100 have very logical, consistent names. We just add 1, 2, 3, 4, 5, 6, 7, 8, 9 to the corresponding multiple of 10. So for example, from 20 to 30, the numbers are 20, then 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. And the pattern continues that way for all the various multiples of 10. So from 30 to 40, it's the same kind of thing. 30, and then 31, 32, 33, and so on down to 40. In this simplified, more logical presentation that I'm half suggesting, the corresponding names would be something like this. 25 would be written 2, 10, 5. 210 representing that digit there, 5 representing that digit there. We're just reading left to right, taking into consideration this is the 10s, that's the 1s. So the logic there is quite consistent, and similarly with this one. So we have the numbers from 1 to 100 now, and we've given names to all of them. So a few examples. This number is 53 because it consists of 50, which is the multiple of 10, plus 3. 5 10s, 3 1s makes 53. In our simplified formulation, that would be 5, 10, 3. This one, 67, or 6, 10, 7, and 98, or 9, 10, 8. So once we have the numbers from 1 to 100 down, then the numbers from 100 to 200, say, are pretty straightforward. All what we have to do is just add 100 to the front. So this number here, which is 6 1s, 2 10s, 1 100, that's spoken how? We read from left to right, so we read 100 and 26. This 2 represents 2 10s, so that's a multiple of 10, the multiple we called 20. So 126. This word and is sometimes used and sometimes not used, or used just a little bit. 126, people often say, with just an N sound to represent that and. I would suggest, in a simplified kind of formulation, to think about 100 as being represented by the word hun. Maybe a little bit short, but short is good. So just like 10, hun is same kind of construction. So this would be hun, 210, 6. Might take some getting used to, but this kind of thing is easier to say, certainly shorter than 154. Hun, 510, 4. 188, 188, or hun, 810, 8. I'll just give some thought to this. It's nice to have short words for important names, especially important names of numbers, ones that you use a lot. If you were counting from 100 to 200, 101, 102, 103, 104, 105, and so on, that 100 that you have to say all the time becomes a nuisance because it's long. And also because we are obliged to say 1, and the 1 is really rather unnecessary. So we're now in control of the numbers from basically 1 up to, say, 200. And now we can have a look at multiples of some other numbers. Now that we have good names for numbers, we can start talking about them a little bit more fluidly. So here are the multiples of 5. What you get when you start with 5, and then you add another 5, and then you add 5, and then you add 5, and you keep on adding 5. That's what we mean by multiples of 5. So 5, add 5, you get 10. Add 5, you get 15, and then 20, and then 25, and then 30, and then 35, and then 40, and then 45. And we can represent those numbers also geometrically in terms of rectangles. And that's a very nice thing to do. We're going to use rectangles which have 5 rows. So 5 times 1, there's that first rectangle. It has 1, 2, 3, 4, 5 squares in it. So it's another representation of 5. 5 times 2, that's that shaped rectangle, that has 10 in it. That's a way of thinking about 10. This way we can get more multiples of 5 just by extending the rectangles in this horizontal direction, always with the same height. So all of these rectangles, these are all multiples of 5, have the same height. They're all 5 rows high. 5 times 1, 5 by 2, 5 by 3, 5 by 4, 5 by 5. These are the numbers 5, 10, 15, 20, and 25. And of course, we can keep going. So very important for the students to think in terms of multiples of a number like 5, in terms of rectangles. Okay, this two-dimensional aspect of numbers which are products goes back to the ancient Greeks. It has a lot to recommend it. After getting down multiples of 5, the next simplest system of multiples are the multiples of 4. Okay. The multiples of 4 are 4, then 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16, keep on adding 4, 20, 24, 28, 32, 36, 40, 44, and so on. These also have representations as rectangles. Now they're 4 squares high, 4 by 1, 4 by 2, 4 by 3, 4 by 4, 4 by 5. These are also ways of representing the numbers 4, 8, 12, 16, and 20 when we're thinking of them as multiples of 4. So here's that number 20, which we also had another way of thinking about that. We thought of that as a multiple of 5 as well. So this is a multiple of 4, it's a multiple of 5, it's also a multiple of 2 because it's an even number, and it's also a multiple of 10. So that's not a problem. Numbers can be multiples of lots of other numbers. And so a number like 20 can have different representations in terms of a rectangle. This is one of them. We could also represent it as a rectangle with 2 rows and 10 columns, or 5 rows and 4 columns. So the multiples of 4 are reasonably easy because we've sort of seen them before. They're really every second one in the sequence of even numbers. So here are all the even numbers. And the multiples of 4 are just every second even number. 4, then 8, then 12, then 16, then 20, then 24, then 28. That makes sense because with the even numbers we're going up by 2 each time. And with the multiples of 4 we're going up by 4 each time. So it's sort of like 2 plus 2, 2 plus 2, 2 plus 2, and so on. Multiples of 4. So students should work their way through these. They should be able to generate these multiples in their head by doing little additions. Then for the next one, what's 28 plus 4? They have to figure it out. It's 32, and so on. And then after multiples of 4, the next natural multiple system is that of multiples of 3. Particularly pleasant pattern, I think. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and so on. Because 3, after all, is many people's sort of favorite number. It's a very nice number to work with. Pretty small. You can easily see what's going on, but it's a little bit more interesting than 2. There's 3 by 1, which is 3, 3 by 2, which is 6, 3 by 3, which is 9, 3 by 4, which is 12, 3 by 5, which is 15, and so on. And so at each stage, we get the next one by adding 3. So for example, the next one after 33, we would get by adding 3. 33 plus 3 equals 36. And how do we know that? Well, you can either sort of do it in your head. You have 33 and then you have to add 3, so 34, 35, 36. And many students will do that calculation that way. But another way for them to think about it is we're adding 3 to the 3 units that are here. So it's really a case of knowing the addition table of what is 3 plus 3. This is 3 ones. Here we have 3 tens and 3 ones. So we're adding these 3 ones to the 3 ones which are already here to get 6 ones. The number of tens in this case doesn't change. So ultimately this is a consequence of this simpler rule that 3 plus 3 equals 6. And so if a student knows this automatically without having to use fingers, then they can do this automatically because 33 plus 3, the 2 3's here are the ones that add to get 6. Similarly, when we get to 36 and we want to add 3, then it's the 6 and the 3 that are combining to give the 9. 36 plus 3 is 39 because 6 plus 3 is 9. That's the essential knowledge that's required. Of course, you can do it by fingers, 36, 37, 38, 39. There we've just added 3. But it's probably better for the student eventually to realize that it's because 6 plus 3 equals 9 that 36 plus 3 is 39. This is 3 tens and 6 ones, and we're adding 3 ones. So the 6 ones and the 3 ones are adding to make 9 ones, and the 3 tens are sitting over there just as they were at the beginning. At the next step, from 39 adding 3 more, we get something a little bit more involved because we have to carry. So 39 plus 3, well, with fingers, 39, 40, 41, 42. And the student should also realize that's because the 9 plus 3 is 12. When we add 9 ones and 3 ones, we get 12, which is actually 10, 2. It's 1 10 and 2 ones. So if we're starting with 39, which is 3 tens and 9 ones, we add 3, then the 9 ones here and the 3 ones here are combining to give us 10 and 2. So one of those tens adds with the 3 tens we already have to give 4 tens. And this is admittedly simplified if you think of this as being 3, 10, 9. So that way 3, 10, 9 plus 3, well the 9 and 3 is giving 10, 2. So 3, 10, 9 plus 3 equals 310 plus 10, 2. Altogether 410, 2. All right, so there's lots of work to be done here, concrete work, working through, calculating multiples, seeing how the carrying goes from one multiple of 10 to the next. Very explicit kind of work that has to be done. Okay, there's weeks of work, months of work for young students in mastering the contents of this particular lecture. All right, the lecture is relatively short, but the amount of material is very large for a young student or a beginner at mathematics. You want to become really familiar with these multiples. And there's perhaps no better way of becoming familiar with them than doing some exercises like this, by counting with these multiples. First of all, counting by ones. That's the absolutely basic skill. Just counting up to some bigger number, maybe to 100, maybe to 120. Maybe if you're very ambitious, to 1,000. Everybody should probably count to 1,000 at least once in their life. Then you can count by twos, count by tens, count by fives or by fours or by threes. If you count by threes, you're not going to quite get to 100. You'll get to 99, and then you'll get past 100 to 102, so you'll actually skip 100. We can solve that problem by going to 120 instead, which is maybe a little bit more fun because there's some numbers there which are bigger than 100 to work with as well. So that's a good exercise. Count to 120 by all of these multiples. And once you or the student has done this enough, then you can work on this more challenging problem, counting backwards from 120. Or maybe you can start with something more modest like 60, which plays the same kind of role. So counting backwards by tens, for example, 60, 50, 40, 30, 20, 10. A little bit more challenging, do it with fours or threes. So you can work on this. Multiples, up and down, multiples of all these numbers. Of course, there's also multiples of 6s and 7s and 8s and 9s, which we haven't talked about. Those are a little bit more advanced. We'll be talking about them later. Next time we want to talk about some word problems using addition. So we've got a bit of skill now with addition. We can actually do calculations. Let's have a look at some problems from sort of everyday life and solve them using our skills. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.